In this episode, we're going to make the confusion matrix feel like a fast, friendly dashboard instead of a scary grid that slows you down during practice questions. When you are brand new to classification, it is easy to get lost because multiple metrics compete for your attention, and the exam can add stress by describing outcomes in dense wording. A confusion matrix solves that problem because it shows you, in one place, what the model said versus what reality was, and every metric you care about can be traced back to those counts. Once you can read the matrix quickly, you stop guessing what precision or recall means, because you can literally see false alarms and misses. You will also learn how a decision threshold can reshape the matrix, which explains why a model can improve one metric while hurting another. By the end, you should be able to glance at a confusion matrix, describe the model's behavior in plain language, and predict how the trade-off changes when you move the threshold. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A confusion matrix is simply a table that counts how often each combination of predicted label and true label occurred. Even though the name sounds dramatic, it is really just a structured tally sheet. One axis represents what the model predicted, and the other axis represents what the real label was, and the exact layout can vary depending on how it is drawn, which is why careful reading matters. The core idea is that there are 4 outcomes in a basic 2-class setting: correct positives, false alarms, correct negatives, and misses. Those 4 outcomes summarize the model's success and failure in a way that is more concrete than any single score. Beginners often try to memorize metric formulas without understanding the underlying counts, and that makes everything feel fragile. When you start from the matrix, the logic becomes sturdy because you can always rebuild the meaning from the counts. On the exam, this is a huge advantage because if you forget a formula, you can still reason your way to the correct interpretation. To diagnose a confusion matrix quickly, the first step is to anchor the meaning of positive and negative in the scenario, because those words are not morally good or bad, they are just labels. In some questions, positive might mean fraud, malware, or anomaly, and in others it might mean approved, benign, or normal, depending on what the model is trying to detect. If you misidentify what positive represents, you can interpret the entire matrix backwards and still feel confident, which is one of the easiest ways to lose points. A reliable habit is to say to yourself, positive equals the condition we care about catching, and negative equals everything else. Then check whether the scenario matches that statement. Once positive is anchored, the 4 outcomes become meaningful. A correct positive is a catch. A false alarm is a flagged case that should not have been flagged. A correct negative is a clean pass. And a miss is a case the model failed to flag. That language keeps your interpretation tied to reality instead of abstract symbols. Because confusion matrices are often shown as a grid of numbers, speed comes from knowing what question you are trying to answer before you start doing arithmetic. Sometimes the exam is not asking you to compute a metric at all, but to describe what kind of error dominates. If the false alarms are large compared to the correct positives, the model's positive predictions are noisy, which pushes you toward thinking about precision concerns. If the misses are large compared to the total number of real positives, the model is failing to catch many true cases, which pushes you toward recall concerns. If correct negatives are enormous, that might simply reflect that the negative class is common, which can make accuracy look inflated even when detection is poor. A fast diagnosis is to compare the 2 wrong cells first, because those are the costs you are managing. Then look at which correct cell is strong, because that tells you what the model is good at. This is a practical reading skill, not a math exercise. It also helps to understand that the confusion matrix is a snapshot at one operating point, meaning it reflects one chosen threshold for deciding positive versus negative. Many models do not output a hard label by nature. They output a score, and the threshold converts that score into a yes or no decision. If you change the threshold, you do not change what the model learned internally, but you do change how often it is willing to say positive. That decision changes the counts in the confusion matrix, sometimes dramatically. A stricter threshold usually means the model says positive less often, which tends to reduce false alarms, but increase misses. A looser threshold usually means the model says positive more often, which tends to reduce misses but increase false alarms. Beginners sometimes assume the confusion matrix is a permanent description of the model, but it is a description of the model plus the decision rule. Exam questions often hint at threshold shifts without using the word threshold, using phrases like becoming more conservative or being more sensitive, and those phrases are clues that the matrix is about to change shape. When you are asked to compute or interpret precision from a confusion matrix, the fastest way is to remember what precision is measuring in plain language rather than recalling a formula from memory. Precision is about how trustworthy positive predictions are, which means you look only at the predicted positive column or row, depending on the layout. Inside that predicted positive bucket, some are correct positives and some are false alarms, and precision is essentially asking what fraction of the bucket is truly positive. If the false alarms are high, the bucket is polluted and precision falls. If false alarms are low relative to correct positives, the bucket is clean and precision rises. The important exam skill is noticing that precision ignores misses entirely because misses are not inside the predicted positive bucket. That can feel strange at first, but it makes sense because precision is not asking what you failed to catch. It is asking how reliable your catches are. If a question describes a team overwhelmed by alerts that turn out to be nothing, that is a precision problem even if recall is high. The matrix lets you see that overload directly. When you are asked to compute or interpret recall, the fast pathway is similar but focuses on the true positive world rather than the predicted positive bucket. Recall is about coverage of real positives, which means you look at all cases that are truly positive and ask how many of them the model caught. In the confusion matrix, the real positive world is split into correct positives and misses, and recall is asking what fraction of that real positive world was captured. If misses are high, recall falls even if precision is excellent, because the model is simply not finding enough of what matters. This is why a model can look clean, producing few false alarms, but still be useless if it misses most true cases. Exam questions often describe this as a model that rarely triggers, but the triggers are usually real, which sounds good until you realize it might be missing almost everything. The confusion matrix is where you confirm whether that is happening. Once you see the miscount, you can explain the trade-off in a grounded way instead of guessing. Accuracy is often present in exam questions as a distractor or as a partial truth, so it is worth learning how to diagnose its limitations using the matrix rather than abstract warnings. Accuracy counts all correct predictions, both correct positives and correct negatives, and divides by the total number of cases. If one class is much more common than the other, accuracy can be high even when the model is failing at the rare class that matters most. In a confusion matrix, this shows up as a huge correct negative number and small numbers elsewhere, which can create the illusion of success. A model that predicts negative almost all the time can achieve high accuracy in an imbalanced dataset while producing terrible recall for the positive class. The exam will often test whether you can spot this by describing a rare event detection task and showing a matrix where correct negatives dominate. The correct response is to shift focus to the errors that matter, which are usually misses and false alarms for the positive class, not overall correctness. Being able to say, accuracy is high because negatives dominate, but the model misses positives, is exactly the kind of clear reasoning that earns points. Now bring thresholds back into the picture, because threshold-driven trade-offs are where confusion matrices become a true decision tool rather than a reporting artifact. Imagine sliding the threshold upward, so the model requires stronger evidence before calling positive. As the model becomes more conservative, the predicted positive bucket shrinks, which usually reduces false alarms because fewer marginal cases are flagged. At the same time, that shrinkage means some true positives that previously crossed the threshold no longer do, so misses increase. In the confusion matrix, you will usually see correct positives decrease and misses increase when the threshold becomes stricter. If you slide the threshold downward, the predicted positive bucket grows, so you catch more true positives, which reduces misses, but you also scoop in more negatives, which increases false alarms. In the matrix, correct positives typically increase and false alarms increase when the threshold becomes looser. The key is that you cannot move the threshold and expect both false alarms and misses to decrease unless the model itself improves. That simple reality explains most metric trade-offs. A strong way to diagnose trade-offs quickly is to connect each matrix cell to an operational story, because the exam loves scenarios that are really about workflow capacity and risk. False alarms consume attention, time, and trust, because analysts or reviewers must investigate cases that turn out to be benign. Misses create exposure, because the system fails to flag cases that should have been caught, allowing harm or loss to slip through. Correct positives create value, because they are true catches, but they also create work, because someone has to handle them. Correct negatives create efficiency, because they are cases correctly ignored, but they can become a misleading comfort if positives are rare. Threshold changes are basically a policy decision about how you want to distribute those burdens and risks. If you have limited review capacity, you might tolerate more misses to reduce false alarms. But if missing positives is unacceptable, you might tolerate more false alarms to increase recall. The confusion matrix is where you quantify that policy decision. Even if you do not compute exact metrics, you can explain the consequences clearly, which is what many questions are really asking. Another beginner trap is thinking that threshold choice is purely technical, when it is often about aligning model behavior to costs, constraints, and goals. A threshold that maximizes one metric may be a terrible threshold for the actual mission of the model. For example, maximizing accuracy might choose a threshold that favors the majority class and ignores rare positives, which can be disastrous in detection tasks. Maximizing precision might choose a threshold so strict that you almost never flag anything, which can be disastrous if the goal is to catch as many positives as possible. Maximizing recall might choose a threshold so lenient that you flood the system with false alarms, which can be disastrous if humans must review them. The exam may not ask you to pick a numeric threshold, but it will often describe goals like minimize false positives or maximize detection, and then ask what happens to the confusion matrix. The correct reasoning is that threshold selection changes the balance between false alarms and misses. If you can describe that balance using the matrix, you can answer those questions without relying on memorized phrases. Because confusion matrices are sometimes presented in slightly different layouts, it is essential to build a layout check habit that prevents careless errors. Some matrices put true labels on the rows and predictions on the columns, while others do the reverse, and the words can be abbreviated or placed in small print. Beginners often assume the layout they saw first is universal, and then they apply the wrong interpretation under time pressure. A safer approach is to always identify one cell you can name confidently by reading axis labels, such as where predicted positive meets true positive, and then label the other cells relative to it. Once you have that anchor cell, you can locate false alarms as predicted positive with true negative, and misses as predicted negative with true positive. This takes only a few seconds, but prevents a major mistake. Exam questions sometimes test this indirectly by presenting a matrix with an unusual orientation and seeing whether you interpret it correctly. A disciplined reader treats the matrix like a map and checks the legend before driving. It is also worth understanding how confusion matrices connect to curve-based evaluations, because you may see references to threshold sweeps even if the question focuses on one matrix. When you vary the threshold, you can generate many confusion matrices, one for each threshold choice, and each matrix gives you a pair of trade-off points, like how many true positives you catch and how many false alarms you create. Curve-based views are essentially summaries of how those trade-off points move as the threshold changes. Even if you do not draw the curve, you should understand the logic that a single confusion matrix is one dot on a broader trade-off landscape. This perspective prevents a common misunderstanding where students treat one matrix as the full truth about the model. If a question hints that the threshold is being tuned, you should expect the confusion matrix to change, which means the best choice depends on what part of the trade-off landscape you care about. Thinking this way also prepares you for questions that ask how performance changes when you become more sensitive or more conservative. The matrix becomes your anchor for that reasoning. Finally, a mature way to use confusion matrices is to look for patterns that suggest deeper issues than threshold choice, because not every problem is solved by moving the cutoff. If a model has both many false alarms and many misses, the issue is likely that the model is not separating classes well, so threshold tuning only moves pain from one side to the other. If the matrix shows strong performance overall, but failures concentrate in certain conditions, the model might be missing features that capture those conditions, or the data might be inconsistent across segments. If correct positives are low because positives are extremely rare, you might need to focus on data representation, sampling strategy, or labeling quality rather than pretending a threshold will solve scarcity. The exam may present a matrix where the trade-off seems impossible and ask what that implies, and the mature answer is that model discrimination or data quality might be the limiting factor. Confusion matrices are not just scoreboards. They are diagnostic tools that tell you whether you have a threshold problem or a deeper modeling problem. This distinction helps you avoid simplistic reasoning that treats every issue as a tuning knob. To close, diagnosing confusion matrices quickly is one of the most reliable ways to stay grounded in classification evaluation, because the matrix forces you to confront what kinds of mistakes are actually happening. You learn to anchor the meaning of positive and negative to the scenario so you do not interpret the grid backwards. You learn to focus first on false alarms and misses because they represent the real costs you are trading, and then connect those counts to precision and recall as two different views of performance. You also learn that accuracy can be misleading in imbalanced settings, and the matrix makes that obvious when correct negatives dominate the totals. Most importantly, you learned how decision thresholds reshape the matrix by changing how often the model is willing to say positive, which creates a predictable trade-off between false alarms and misses. When you can explain that trade-off in plain language and tie it to the numbers in the matrix, exam questions stop feeling tricky because you are no longer guessing what a metric name means. You are reading the model's behavior directly and reasoning clearly about what changes when the threshold moves.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.